Hello everybody, this is my first math video. I would like to show you two problems that uses modular arithmetic to solve, and I will start by introducing what is modular arithmetic. In its essence, it is basically this formula. It's not a formula, it's just how you write it. It reads like A equals to B modulo n. And what that basically means is when A divided by n, B is the remainder, okay? If that makes sense. And A or B are always integers, and n are natural numbers that's greater than 1. This is another way to express it. A equals K times N. K in this case is relatively irrelevant, I would say. You don't see that in the actual thing. And so N plus B, and in this case still B is the extra number, the remainder after a product of these two. So if that didn't make sense, I'll show you an example. For example, 16 equals to 1 modulo 5. So when 16 divided by 5, and there will be a remainder of 1. So 3 times 5 is 15. 16 minus 15 is 1, so that's where the remainder came from. And I can give another example. 25 is equal to, let's see, 4 modulo 7. So have 25 divided by 7, that just be 7 times 3, 21, and 25 minus 21 is 4, and so that's where that comes from. And this number can never be greater than the modulo, the n. B can never be greater than n. Very intuitive, because you can't get this can't equals 8, because if it's equals 8, it equals 1, if that makes sense. I hope that makes sense. And the last example is time. Time, that's one of the place where modular arithmetic takes place in our daily life. It's time. So for example, we have a clock. It's a very vast circle anyways. This is 12, 3, 6, and 9. Okay, so for example, if you're at 6 o'clock, 6 o'clock plus 7 hours doesn't equal 13th hour, it equals 1, okay? It equals 1. So our time is functioned in this modulo 12. Let me write it down. 6 plus 7 is equal to 1 in modulo 12. So you can think of whatever modulo, you can think of it as a circle, so it goes around and around and around and around. Yeah, and now we're going to jump into the problem, and I will show you the first problem. So this is our first problem. I got this problem from Solving Mathematical Problems, by Terence Tao. I think he wrote this in high school, and it's compilations of math competition problems. And even though I don't attend any math competitions, I still find this enjoyable, so I highly recommend the book. And this problem is the exercise 2.3 in the book, and it doesn't have a solution in the book, by the way. So show that the equation x to the 4th plus 131 equals 3 times y to the 4th has no solution if x and y are integers. The first step I would do is to just list out the first few powers of 4 and see what kind of pattern you can find, and use that pattern or a period to use modular arithmetic. So let's follow that. So the first few powers of 4, 0 is 0, 1 is 1, 2 is 16, and then 3 is 81, 4 is 256, and then 5 is 625, 6 is 1296. And then 7 is 2401. Okay, so this is our first 7 powers of 4. And I know it's 0, 1, 6, 1, 6, 5, 6, 0. Looking just at the last digit, there's no period or a pattern that's consistent. And so we can think about it, and you're now using modular arithmetic. We can think about it in another modulo. Because when we're looking at the last digit, we're in modulo 10, and now we can switch to modulo 5, see what we can find. If we look at all these numbers in modulo 5, okay, it will be 0, 1, 1, 1, 1, 0, 1, 1. So as we can see, there's no, even though there's no period, we can still conclude that when any number raised to the 4th power equals to 0, either 0 or 1 in modulo 5. That's a very important find for this question. And so the next step, now we can know that x and y in modulo 5 can only equals either 0 or 1. So either 0, 1, either 0, 1. And let's look at this, 131. 131 equals to 1 in modulo 5. And now we have concluded, reduced that in modulo 5, this equation has only 4 possibilities, because x can have 2 possibilities and y can have 2 possibilities. So there's only 4 possible equations that we can come up with. And let's list them out. For example, when x equals 0 plus 1 equals 3 times, let's see, 0. So this is when the situation when both x and y equals 0 in modulo 5. And now we go to when x equals 0 and y equals 1. Okay, x equals 0, oops, and y equals 1. And now x equals 1 and y equals 0. And now x equals 1 and y equals 1. Okay, so now as you can see, these are the only 4 possibilities for this equation in modulo 5, and none of them make sense. You see, 1 doesn't equal to 0, 1 doesn't equal to 3, 2 doesn't equal to 0, and 2 doesn't equal to 3. So through proving that all the possible combinations of x and y in modulo 5 does not stand, also proves that there are no integer solutions. I hope you understand that, and this was a very fun problem to solve. This is problem number 2, and it's from the same book. It's one of the example problems, and so it has the solution in the book, if you ever get the book. And the problem states that prove that for any non-negative integer n, the number 1 to the n plus 2 to the n plus 3 to the n plus 4 to the n is divisible by 5, if and only if n is not divisible by 4. So this is asking you to prove a really interesting property of number theory, and it looks quite like Fermat's last theorem, if you don't know. A to the n plus b to the n equals c to the n. I promise you don't have to use elliptic curve or modular form to solve this problem. You only need modular arithmetic, which is what I just introduced you to. And I was planning to solve this for you, but I really want to keep this video short, and so think about it. I'll give you a hint, which is put this in modulo 5. Okay, raise each of the numbers to a power 1, 2, 3, 4, whatever power, and then list them, and then put them in modulo 5. See what you find, and see what kind of pattern you find, and that might help you to prove this statement. So this is for today. If you want me to solve this problem in the video, I'll do it. If anybody watches the video at all, which is unlikely. So see you next time. Bye bye.